circles.
Whenever you're ready.
You want
Oh, we do.
for people to get food in.
Oh,
We can live stream. There's a live stream, so we can watch it on our phones.
Yeah.
Live stream.
Yeah, I'm watching it too.
Maybe I should plug in and listen to it. Listen to it on there. Is it delayed? Turn the audio up and we can get a really good back going.
Yeah.
Because my phone
Oh, that's cool. We actually have a built-in system in here where there are these things you can hold up to your ear. It's like headphones that will just tell people who have low hearing to be in the room. People never use it.
Yeah. So when's my 3:30? Yeah, 6:17. Yeah. Thank you.
A lot of work in real time to get it from sound to words.
Josh, can we start?
Yeah, it's quite fast.
Yeah. Hi everyone, thank you for being here. We are very happy to welcome Daniel from Los Alamos National Laboratory. He's a Richard Feynman postdoctoral fellow starting 2018. He's a graduate from University of California, San Diego. He'll be giving a talk about using machine learning in seismology. Daniel?
Okay, great. So the microphone's working okay? Perfect. All right. Well, yeah. Thanks for inviting me to come here. I don't actually get to make it out to the East Coast very often. It's the first time I've been to Boston. So I'm excited to be here and to meet everyone and to present some of my research related to earthquake hazard and source dynamics using machine learning. So I'm an observational seismologist, and in my research, I'm focused mostly on observational seismology and earthquake hazard analysis. And I use kind of data-driven or machine learning techniques as a tool. And I think in my abstract I had 3 applications I was going to go over, but when I was writing this talk it became clear pretty fast that that was going to be a little bit too ambitious for the time slot. So I'm going to just focus on 2 specific applications in my research today. The first is a problem related to ground motion prediction. using machine learning to measure the influence of earthquake stress drop on ground motion amplitudes for earthquakes in the San Francisco Bay Area. And the second application I'll discuss is a collaborative effort between some scientists at Los Alamos and at U.S. Geological Survey, doing a kind of a systematic analysis of the waveform features of large magnitude earthquakes offshore Japan, and trying to understand the observational limits of rupture determinism, which has, and the USGS is interested in that work because it has some pretty important implications for real-time hazard analysis and earthquake early warning, and I'll try and touch on those as we go along. But before we get too far, I just want to acknowledge some of my collaborators in this work today. So one is my PhD advisor at Scripps, Peter Shearer, and then some of my LANL collaborators, Paul Johnson and Kipton Barros. And then I've been working most closely with Joan Gumberg at USGS in Seattle. And so these guys have been really instrumental in guiding my research and working on some of the stuff that I'm going to show today. So this slide is just kind of an introduction to machine learning. It's probably a bit superfluous given the audience at MIT, but so just to give a bit of background, in neurosciences we're really starting to be kind of a data-rich field. We have larger and larger, more complicated data sets, and we have to start thinking about how to make sense of these data sets in more sophisticated ways. And so in my research and the way I use machine learning, I use it as kind of a statistical framework for testing scientific hypothesis, for kind of removing human biases that might be present about thinking about different problems that are relevant to the earth sciences. And then you can also use it to kind of help uncover hidden features within data sets that might not be apparent to the human eye. But machine learning, it's not going to solve all of our problems. It's not really a substitute for a theoretical understanding of the physics of the problem at hand, or it's not a substitute for hands-on experience in working with real data sets. And in fact, having a good, solid physical basis for the problems you're trying to focus on really helps guide machine learning methods and make them kind of more powerful for the applications you're interested in. And so kind of broadly speaking, you can subdivide machine learning into kind of two different subfields. One is supervised learning, where the objective is to develop some sort of predictive model based on input and labeled output data, and you're trying to make predictions. You train your model on some subset of data, and you want it to be generalized to a different data set to be able to have some predictive validity. And then in unsupervised learning, there's no kind of labels on the output data. You're just really trying to understand structure or groups within the data sets. And so today, I'm going to focus mostly on the supervised learning aspects and applications to seismology. And I'm going to start with machine learning and its application to ground motion prediction, and in particular focus on the effects of source complexity in ground motion. So from a physical perspective, the observed ground motion can be thought of as a convolution of source effects. So what happens during earthquake rupture to generate seismic waves, path effects, so what happens to those seismic waves as they travel from the source to the surface, and then side effects, so what happens to these waves as they actually near the surface and kind of encounter the soft sediments and are sometimes distorted. And so today I'm going to focus mostly on the source side of things, although a lot of the techniques we're going to discuss have relevance for studying path effects or side effects more generally. And so the two observable features that have kind of the strongest influence on ground motion that are really source effects are magnitude and stress drop. And magnitude has a pretty intuitive effect on ground motion, in the sense that we expect larger magnitude earthquakes to have systematically higher ground motion amplitudes, and so that kind of makes sense, and that's pretty well understood and pretty easy to model. But stress drop has a kind of a more complicated influence on ground motion that's magnitude dependent and frequency dependent and propagation effect dependent, and that's kind of going to be the focus of the first half of my talk today. And so when we think about earthquake size, usually we think about a static measure, so something like seismic moment or magnitude that's related to the total fault area and the slip of the earthquake. But earthquakes of comparable size can vary pretty substantially in their dynamic source properties. And so the time scale over which they release their energy and their moment. And so that you can just see that if you plot the natural variability in moment release for different large earthquakes. You can see they all have this kind of characteristic pulse-like shape, but that the time scale can be very different even if the magnitudes are relatively comparable. And so in the far field, this translates into variations in the observed displacement pulse, because the far field displacement is proportional to the moment release, and so these differences in the time scale and the amplitude will show up in the far field displacement in terms of differences in time scale and amplitude in the time domain. And then in the frequency domain, this kind of corresponds to a classic kind of, they call it a Brune type spectrum, where there's this where they roll off at a corner frequency that's inversely proportional to this time scale. And so stress drop, at least measured dynamically from a source spectrum, is a bit of a derived parameter, and it's often kind of considered equivalent to a static stress drop, which is proportional to a slip divided by source radius. But it's really only the case for kind of special sorts of earthquake of crack-like ruptures, and it's this formula, this Eshelby relationship, is really only appropriate for a circular rupture or a circular earthquake source. But in any case, this proportionality between stress drop and corner frequency cubed, you can think of stress drop as a sort of parameter that measures variations in the source frequency content of different earthquakes. And so earthquakes with higher stress drop are the ones that are kind of enriched in high frequency energy compared to earthquakes with lower stress drop. And so in terms of ground motion, they should tend to have systematically larger ground motion amplitudes, because for fixed magnitude or fixed moment, the area under this displacement pulse is fixed, but the time scale is shorter for the high stress drop events, and so you'd expect higher ground motion amplitudes to be associated with higher stress drop events. And so you can think of one way to think about this is in terms of ground motion prediction equations. And so traditionally, a ground motion prediction equation is just it's a linear regression relationship. It looks something like this, that predicts median ground motions and their uncertainties. In some ground motion intensity metric, like peak ground acceleration is a common one, as a linear function of magnitude and distance, and sometimes there are side effects, but usually the basic functional form is something like this. But this equation doesn't know anything about the stress drop of the event. And so differences in stress drop from event to event will show up in ground motion space. So if you plot peak ground acceleration as a function of distance, an event with a higher stress drop will tend to have correlated residuals that are higher than the GMPE would predict, and conversely, events with low stress drop would have negative residuals here. And so, as I mentioned, the traditional GMPEs are really these linear regression-based models that will account for the first order effects of things like magnitude, source receiver distance. Sometimes they'll try to incorporate a side effect parameterized in terms of, for example, the shear wave velocity in the upper 30 meters of the Earth's crust. That does a reasonable job of at least first order proxy for side effects. But in the real Earth, there are actually a lot of more complexity than can be kind of simply parameterized in terms of a linear regression model. There's interactions between source effects and side effects and path effects that are pretty difficult to parameterize in terms of a linear regression model. And this is where machine learning can come in to help us study these higher order complexities in greater detail. And so that's what we did in this study that was published in BSSA earlier this year, is to use a machine learning technique called random forest to study the influence of stress drop on ground motion for pretty small to moderate magnitude events in the San Francisco Bay Area, so magnitude 1.8 to 5. So just a bit of background on ground motion prediction. So it's actually, if you think about it, it's really a classical supervised learning problem in the sense that the objective here is just to train a model, so that's a GMPE, to predict ground motion given an arbitrary set of input features. And so a random forest is a specific type of supervised learning method. It's what's called an ensemble method that combines multiple models together. And it works, you can use it for nonlinear regression, which is the case of a ground motion prediction equation, or classification. And so an ensemble method is basically the model equivalent of wisdom of the crowds. You're trying to combine multiple models that have, different perspectives on the problem, and the ensemble average is more robust by doing that. And so in a random forest, each base model is a regression tree. You train the individual regression trees by recursively partitioning or splitting the feature space into different regions with similar output values. And so in the case of ground motion, your feature space could be something like magnitude and distance, and you'd be trying to predict something like peak ground acceleration. And the random part of the random forest comes in training each of the individual trees, because each of the trees sees a bootstrap resampled copy of the input data, and also incorporates random feature selection during its training process. And that essentially, these two things kind of decorrelate the different trees in the ensemble, and it makes the final ensemble average much more robust. And so this is what the basic functional form of the GMPE that we used in our study looks like. It looks a little bit complicated, but the key thing to keep in mind about it is that so the base part of the random forest accounts for the nonlinear and interacting effects of magnitude and distance, but it also kind of iteratively learns the individual contributions of the events and the stations that are not accounted for by the magnitude and the distance. And so the key thing to keep in mind about this equation is that these delta PGA terms are essentially represent kind of a measurement of how much an event, how much higher or lower the ground motion of an event is compared to what you'd expect for a typical event at that station, at that magnitude, and at that distance. And so this is just kind of a schematic workflow of how this works in practice. So you input your data set at the top. So this would be something like peak ground acceleration as a function of magnitude, distance, event, site, and you could add more features if you wanted to, so on. And then and that's kind of the input stage, and then you'd send a bootstrap resampled copy of that data set to each of the individual trees in the forest, and then they'd each be trained to independently predict peak ground acceleration, and in the end, those predictions are aggregated in an ensemble average, and that's the final output PGA prediction. And then the event terms and the station terms are iteratively learned from the model residuals. It's something, if you've encountered mixed effects regression in linear regression problems, it's kind of analogous to that. But the key thing this allows us to do is that these events that have these delta PGA or event residual terms, the ones that have positive delta PGA are events with larger than expected ground motions. And so this allows us to kind of quantify events that are anomalously high in ground motion, and then in turn we can compare these ground motion residuals to things like stress drop. And so that's what we did in this study of the San Francisco Bay Area. We were using a pretty large and well-recorded data set from the Northern California Seismic Network. So it's about 5,000 magnitude, 1.8 to 5 earthquakes occurring in the Bay Area over the past 15 years or so. And the first step here was, because we don't actually have independent measurements of stress drop for these earthquakes, is we had to actually go out and measure stress drop. And so we used this P-wave spectral decomposition technique that I'm not going to have too much time to go into today, but it tends to work pretty well for large and well-recorded data sets where each earthquake is observed by many stations, and each station records many earthquakes, which is definitely the case in the Bay Area. All these little purple triangles that are hard to see are actually the stations, and the black dots are the events. So there's a lot of earthquakes and a lot of stations. So just very briefly, this spectral decomposition method, it was originally used to measure stress drop for more than 60,000 very small magnitude earthquakes in Southern California in the 1990s. The basic idea here is that if we work in the log frequency domain, it's possible to decompose the observed P-wave spectrum into a sum of relative source, site, and path terms. And so this distance or path term accounts for both geometric spreading and attenuation along the travel path, but because this decomposition is kind of in relative space, there's also this kind of hidden path effect that is common to all sources. And so you need to develop some sort of empirical correction term to correct for path effects like near source, average near source, and average near receiver attenuation if you want to use the source terms to compute corner frequencies and stress drop. And so this improvement in the algorithm that we implemented in 2017 really focuses on this EGF estimation step. For example, we're allowing for smooth variations in attenuation properties, and there's no kind of built-in assumption of self-similar stress drop scaling and so on. So anyways, that's kind of a talk in of itself, but this method tends to work pretty well for large data sets like this one. And so these are the results that I'm plotting here in map view. So each dot here corresponds to an individual earthquake, and the bluer colors are the higher stress drop events, so they're enriched in the high frequency energies, and the redder earthquakes are the ones with lower stress drop, so they're kind of depleted in high frequency energy. And you can see there's some pretty visible spatial coherence in the stress drop distribution. For example, there's a cluster of kind of low stress drop events at this Mount Diablo thrust and Calaveras fault step over region, and then there's a cluster of high stress drop events at the junction between the Hayward and the Calaveras fault, and you can pick out a bunch of other patterns all around the Bay Area. But the point of this study wasn't really to measure stress drop, it was to compare stress drop to ground motion amplitude. So the next step was just to measure peak ground acceleration from the same set of stations and compute those event residuals using the random forest GMPE. And so I guess one thing to keep in mind here is that the stress drop measurements are actually we're using P-wave spectral decomposition using the vertical components of these NCSN stations, but peak ground acceleration tends to come from the S wave. So we're actually measuring two different parts of the waveform here. So with that in mind, this is what the results are. So on the left, I'm plotting the stress drop distribution as before, and on the right, I'm plotting the analogous event residuals. So the events with higher than expected ground motion for an event of its size are the bluer ones, and the ones with lower than expected are the ones with the redder colors here. And so you can see there's a pretty good correlation visually between the areas with high stress drop and the areas with high ground motions, and the areas with low stress drop and the areas with lower than expected ground motion. We can also plot this, see how this correlation varies as a function of magnitude. So that's what I'm plotting here. Each of these individual panels, I'm plotting the event residual, ground motion on the y-axis, and stress drop on the x-axis. And then each panel corresponds to a different magnitude range. So these are the smallest earthquakes, a little bit larger, and the largest earthquakes in our data set. And so there's a pretty strong correlation between stress drop and peak ground acceleration, especially once you get to about magnitude 2.5 or so. And so that's a pretty important takeaway, because that means that stress drop is explaining much of the inter-event variability in ground motion that's not accounted for by most GMPEs, especially once you reach large magnitudes. For the smallest magnitudes of the data set, there's still a correlation, but it's weaker, and that makes sense if you think about the typical frequency content of a smaller magnitude earthquake is much higher than the typical frequency content of a large magnitude earthquake, and so it's more sensitive to path attenuation. And so in ground motion space, the relative variations in the source properties is damped out, and so it has a weaker effect on the ground motion amplitude. Yeah.
What band are you measuring PGA?
It's in the PGA is in the below 30 hertz band. So.
And how does the relationship between that band and the corner frequency of the earthquake?
Yeah, that's a really good question.
Because the stress drop. If you're measuring below the corner frequency or above the corner frequency, then
yeah, that's essentially what accounts for this. In the sense that for the when you're measuring stress drop, you've done some sort of a correction for attenuation along the travel path and the sight path, and when you're measuring peak ground acceleration, you're not. So, so essentially,
what's radiated is going to be frequency dependent.
Exactly.
And it's going to be a function of stress drop. So that's which is a function of corner frequency.
Yeah. So it's as soon as you kind of bump up against the limits of so once the corner frequency is essentially becomes kind of damped out by the propagation effects, then that's when you expect the correlation between stress drop and peak ground acceleration to break down. So you're exactly right. That's kind of what's happening here. So you said it better than I could have said it. But of course we know that, so we saw there's a pretty strong correlation here, but the correlation doesn't necessarily imply a causal link, and so you want to make sure you check for other potentially confounding factors that could be controlling this correlation. So for example, if stress drop increased significantly with magnitude or increased significantly with depth, then it could be that a depth dependence is really what's causing this correlation. But it turns out that if you kind of correct for, there's a very slight trend in our data set for stress drop to increase with magnitude, and a kind of a more significant trend for stress drop to increase with source depth. But even if you correct for those factors, the correlation remains. And so this implies that you can't prove that this is a causal effect, but it does imply that this correlation is really a source dynamic effect and not really just caused by something else like depth or magnitude or so on. One other interesting observation that I don't have a great explanation for is that main shocks, if you define the main shock to be the largest event in a given earthquake sequence, the main shock tended to have systematically higher stress drop and associated systematically higher ground motion than aftershocks. And so these plots on the left that are a little bit hard to see are showing that if you compare a main shock event and an aftershock event at equivalent magnitude, the main shock will tend to have systematically higher stress drop. And if you break it down sequence by sequence, within a given sequence, the main shock event will tend to have systematically higher stress drop and ground motion than the aftershocks and foreshocks within that sequence. So I don't have a great physical explanation for that, but it's worth following up in down the line. It could be that the main shocks are occurring on some sort of pre-existing experity and the aftershocks are kind of not, but I don't, that's just kind of wild speculation on my part. So this initial study is kind of a good first step because it helps to quantify, this basic intuition that we had between how stress drop should influence ground motion amplitude. But kind of in its current form, it's not really of any sort of practical significance because it was really focused on magnitude 2 to magnitude 4 earthquakes, which are, frequent, which helps in terms of doing model development and in terms of doing kind of a statistical analysis, but they're not really the ones we care about from a hazard perspective. So it could be that there's a very different relationship between stress drop and ground motion at large magnitudes. And then another important thing is that this is kind of the simplest form of that random forest GMPE in the sense that the only input features are really magnitude and distance, but you could, in future, you could, generalize the random forest to try and deal with kind of more complicated ground motion problems that might arise at higher magnitudes. And so that's really the power of this type of framework is that it's really easily extendable to solve any sort of more complex problem in ground motion prediction. So one thing that you could try and do is you could use this same basic framework to measure how much things like finite fault effects or rupture dynamics, rupture directivity actually influence ground motion. You can also test the non-ergodic ground motion models, essentially where the predicted ground motions vary as a function of source region. You can see whether that's kind of consistent with your data set. And so you can really use this same basic framework to measure and develop models that incorporate physical features that aren't really easy to parameterize in a linear regression framework. And so I think in future I'm going to try and work on this problem a little bit more using some of the strong motion data sets from California, Central and Eastern US, and globally to try and develop some of these data-driven GMPs and also incorporate. We're still, I mean, one limitation here is that we're kind of data limited at large magnitudes and at close source receiver distances, and so you can try and incorporate results from simulations into empirical data sets and try and balance that out. So for the second part of this talk, I'm going to transition here, and so I should mention at the outset that these results, this is kind of work in progress. It's a collaboration between scientists at Los Alamos and at the U.S. Geological Survey, and so this is there is no kind of published result associated with this work, but I'll just give you kind of the preliminary result of our analysis of P-wave features of large magnitude earthquakes. In particular, we're interested in the details of the rupture onset. And so classically, these kind of shear crack models of rupture, which is how you usually think of earthquakes, they're typically self-similar in the sense that their rupture properties and their growth properties are scale independent. So small earthquakes behave the same way as large earthquakes. But it's still kind of an unresolved question, and it's an important one in earthquake physics, is what actually controls the final size of the earthquake? What is it that differentiates a small earthquake and allows it to grow into a large earthquake? And conversely, what makes a small earthquake stop before doing so? And from an observational seismology perspective, we need to know if there is something that controls the final size of the rupture. Is it actually observable? Does something that happens during the rupture onset, is there actually something observable that controls the final rupture characteristic? And so two kind of end-member conceptual models that are useful to keep in mind when thinking about this problem are deterministic and cascading rupture models. And so by determinism, it's this notion that somehow earthquake size is controlled by nucleation or the early rupture process itself. And the idea here is that somehow earthquakes that start with a strong initial kick, so physically this would be a high energy flux or energy release rate into the crack tip, will tend to rupture farther. So this is a notion that was put forward by Ellsworth and Rosa in '95 and Io before that. And schematically, it would go something like this. With this yellow rupture, you have a strong or energetic rupture onset, and so it will tend to rupture a great distance, whereas if you have kind of a weak or energy depleted rupture onset or nucleation phase, then it will tend to be a small rupture. And then what's kind of less well known is that actually in these kind of earthquake early warning algorithms, they implicitly assume some sort of rupture determinism in the sense that they're using a kind of a very small snapshot of the waveform and trying to rapidly estimate magnitude. And so they at least are assuming some sort of probabilistic form of determinism in the sense that something that's seismically recordable within 2 or 3 seconds is able to forecast the final event size of a large magnitude event. The contrasting point of view is a cascading rupture model. These are also called stochastic rupture models, in which the final size of the earthquake isn't controlled by the nucleation or the rupture onset process, but it's controlled essentially by anything else, and it's specifically controlled by the presence of barriers to rupture. So these can be geometric or rheological or geological and so on. So if you have an earthquake that happens to occur on a fault that doesn't encounter a lot of barriers along it, it'll rupture into a large earthquake. And conversely, if you have an earthquake on a fault that has a lot of barriers, then it will end up being a small earthquake. And so the idea is that there might be some differences between nucleation or onset processes in different earthquakes, but they're not large enough to significantly influence the final earthquake size. And this would have important repercussions in the sense that it would be impossible to forecast the final earthquake size while the rupture is in progress unless somehow you perfectly characterized the presence of these barriers a priori. So this is kind of the question we're really focused on here today. We're trying to study the seismic signatures of the rupture onset that help us give insight into this type of problem. And so the observational limits of determinism or lack thereof are really important for earthquake early warning and for real-time hazard. And so I'm going to focus a lot on those implications today because that's what I've been working with most closely on with my collaborators at the USGS. So to give you an idea of how this might fit into the earthquake early warning, this is a typical workflow for an earthquake early warning system. This chart here is for Shake Alert, which is the one that's it's on the Western U.S. It's in prototype right now. If you kind of work with these guys, you can get it on your cell phone, but if you don't work with these guys, you can't. So we had a meeting yesterday looking at the most recent results. But anyways, the basic workflow here is that first the system kind of is kind of in a latent phase, but once the signal amplitude becomes large enough at a number of stations, the event module triggers, and then once the event module triggers, you can usually come up with an initial event location pretty fast by just using the move out across stations. Usually, at least in California, we tend to ignore the depth, and so we're just really interested in the epicenter and the origin time of the event. And then, so that's one of the easier parts of the algorithm, but it starts getting trickier once you have to estimate the magnitude in real time. And so usually this is done using some sort of measure of the waveform amplitude or its characteristic period. And then with this initial source estimate in hand, the next step is to actually predict ground motions. And so you use some sort of GMPE in the current source estimates of the magnitude and its location, and you can generate a shake map of predicted ground motions as a function of space. And if these ground motions are high enough, then you might consider issuing an alert to different regions telling them that strong shaking is coming. And then in real time, these things tend to be updated and recomputed. And the one thing is, like, once you actually issue an alert, you can't really take an alert back, so you want to be careful.
I assume step 4 doesn't have stress drop in it yet?
Oh yeah, no, this does not have stress drop in it, and that's possibly a problem because it doesn't have stress drop, and the GMPEs are usually pretty approximate, and they haven't. Yeah, there's actually a question. I would say steps 3 and 4 are hard science questions. Step 5 is a hard social science question. So yeah, there's a lot of research in progress on these two steps, and the one I'm interested in both. The one that has direct relevance to the work I'm discussing today is actually step 3. So estimating magnitude using a small snapshot of the waveform amplitude.
How does this methodology compare with the tsunami warning system in Japan?
They're actually kind of coupled. What's nice about tsunami warning is that you have more time.
Yeah, but they failed miserably, right?
Yeah, and part of the reason why it failed is because they got this step wrong. So this was a classic case, and I'll actually show you some data from this earthquake later. This is a classic case where they underestimated the magnitude, and that's going to be a problem whether you're trying to predict ground motion or tsunami amplitude.
This fault just kept growing.
Yeah, and so that's an issue that we're still working on. And one of the big issues is that it's the largest event in the data set, and it's the largest event in the data set by a lot. And so it's not clear if it's like an outlier or if it's just where the methods aren't working for that. But So the way this kind of works in practice is that they take a quick snapshot of the waveform after the P wave arrival. So the typical snapshot is about 3 seconds, and they use some feature derived from this 3 seconds to predict magnitude. And so what I'm plotting here are normalized amplitudes of waveforms for different magnitude earthquakes from magnitude. This Tokachi event in 2003 all the way down to a California earthquake, 2.8. And so you can see there's characteristic difference in frequency content, and then conversely, if I had not normalized the amplitudes, this would be way larger. And so you could imagine this actually might work pretty well. This is a pretty easy problem. We can look at differences in frequency content, we can look at differences in amplitude, and we should easily be able to tell the difference between a small earthquake and a large earthquake. But in practice, so you tend to use peak ground motion or pulse duration to try and do this, but in practice this is a much harder problem than it looks at, like just with this picture, and that's the reason why there are many different earthquake early warning algorithms out there, and they all have their strengths and limitations, and they can't really agree on how to do this properly because with real data and noise and real-time data streams, this becomes pretty tricky. And so there's no general framework that's been adopted to date. And one of the reasons for this is that actually the data processing choices have a pretty strong effect on the algorithm performance. And so usually a lot of these algorithms tend to use displacement data, but in practice, on the strong motion stations that don't clip during a large earthquake, you're recording acceleration data. And so you have to doubly integrate the acceleration data stream to displacement, and you usually apply some sort of bandpass filter to try and stabilize that. But the bandpass filtering can have can leave some artifacts in the data set, such that if you get some sort of nice predictive scaling, for large magnitude events, there's some saturation at low magnitudes caused by these filter effects. And the problem gets worse at high magnitudes because you not only can have filter effects at high magnitudes, that kind of the converse of this problem. If you plot some feature as a function of magnitude, you get break in scaling at high magnitudes, but this can also be controlled by the fact that your time window length isn't long enough to record the characteristics of the earthquake source, or the fact that these strong motion stations really just aren't sensitive to the low frequencies that are really important at large magnitudes. And then a third problem is that we're trying to estimate in real time, we're trying to estimate the magnitude of an earthquake, but what we have is a set of recordings across a set of stations. And if there's a lot of within event variability, it's not clear what you do with all these different observations. You just take an average and hope that you can beat down the scatter by taking an average, or are there better things we can do here? And so if we step back and think about it, it shouldn't be surprising that these real-time algorithms are, this is kind of a challenging problem. And some of these things are actually correctable in the sense that there's a bit of an outdated emphasis on making sure these algorithms work really, really, really fast. And that's from the time when these algorithms were developed 15, 20 years ago, when the computing power was much less than what we have. So we can actually focus on being a little bit more precise at the expense of computational efficiency these days. One other problem that's also fixable is the sense that a lot of these algorithms are kind of overfit to their training data, in the sense that they have some data set that they're working with, and they're focused on fitting it as well as possible. But they haven't really tested whether they're actually overfitting the data set that they have, and whether it actually extrapolates out to for example, higher magnitudes, or for example, to a different region that you might want to apply it to. I mentioned earlier that the strong motion stations don't record very well at low frequencies. And then that's kind of related to this problem that large earthquakes are rare, and so there's this tendency to try and fit your data set. If you just do straight linear regression, you're going to fit the low magnitude earthquakes, which are common, and you're not going to fit the high magnitude earthquakes, which are not very common. And so this is where machine learning can come in and potentially help us out here. And it can help in kind of a number of ways. For one thing, you can use kind of various feature extraction techniques to try and understand the best ways to compress the raw waveform signal into a set of predictive metrics. Feature selection is related, and it's just which of those metrics are actually the ones we want to use in a real-time algorithm. And then these are kind of a little bit harder problems, but ones you can potentially make some headway with is dealing with that class imbalance problem, and then also trying to mitigate site and site effects using the full network of observations. And so for this problem, we're using a very large data set of earthquakes, so magnitude 4 to 8, occurring on and offshore of Japan over the past 20 years. This corresponds to about 120,000 vertical component waveforms that are recorded on the KeekNet. The KeekNet actually has twin borehole and surface stations, and we're focusing at first only on the borehole stations, and we're doing this to kind of minimize the site effects and the near surface effects, so we end up with really clean waveforms. And so we're extracting kind of various types of features, related to the amplitude and duration of the waveforms, following the P wave arrival. And we're interested in which of those features are actually the ones that are most predictive of earthquake size, and which ones, and in particular, how long does it take to distinguish a large magnitude earthquake from a small magnitude earthquake. And so just to give you an idea of what the data set we're working with, this is an example of the waveform from the Tohoku earthquake. It's actually a magnitude 8.7 by Japan's measurement. People will disagree about that, but in any case, it's better to just use a consistent magnitude scale. And so what's actually recorded is the acceleration waveform, which is the top plot here, but then you can also compute the velocity waveform and displacement waveform after integration. And then what you want to do is, in practice, you want to measure some sort of feature as a function of time from the P wave arrival. So this is just one of the simplest features you could imagine, which is the peak ground displacement as a function of time from the P wave arrival. So it kind of has this slow linear increase and levels off, and that corresponds to this. But eventually, for a large magnitude earthquake, it'll keep increasing. For a small magnitude earthquake, it'll basically stop. Okay, so with that in mind, this plot's kind of complicated, so let me walk you through it here. But so this is the results for peak amplitude, or peak ground displacement. So that's just the kind of the peak amplitude of the displacement pulse. We've done so this depends kind of to first order of the hypocentral distance, and so we've done a kind of a 1/r distance correction, which actually turns out to be the near optimal distance correction if you do kind of an independent multivariate regression analysis. But anyway, so these are normalized to be 10 kilometers distance. We've excluded all S-wave records, so this is only recordings that are P-wave only. Each dot in each of these panels corresponds to an earthquake, and the error bars correspond to the within event variability across stations. Yep?
Can I ask an interpretation question? If
Sure.
I take your, say, 0.5 second one there,
Yeah.
the interpretation, right, would be that at 10 to the minus 2 centimeter displacement, you may have a magnitude anywhere from 4 all the way up to 6,
Yeah.
going horizontally across.
Yeah.
Okay.
Yeah, so there's two ways of looking at this plot, and it depends on what you, it depends on your point of view. So kind of from the other perspective, if you're actually training a model to a real-time algorithm, you want to flip the x and the y here. But from a physical perspective, it's a magnitude something event is producing this. But from an observational perspective, you have this, what's the magnitude? So it depends on your perspective. And so each of the panels here correspond to a different length of that time window. And so this is the shortest time window. We're only using the first 0.5 seconds of data. This is the longest time window. We're using full 10 seconds of data after the. You can actually keep extending this if you want. But one of the issues if you keep extending this, complicates it, is that the longer you extend this, the more records you lose in terms of the S wave coming in, or you have to do something about the S wave coming in. So there's a trade-off. But in any case, so you can see that the model, there's a kind of a pretty stable linear relationship between for about magnitude 4 to magnitude 7 or so. That stabilizes pretty quickly, so about 1.5 to 2 seconds afterwards. But there's still some problem at large magnitudes in the sense that they tend to be underpredicted. But this problem it gets a little bit better with time window length. So the longer we record, this problem gets, for example, it's a big problem at 2 seconds. It's a less big problem, but still a problem at 10 seconds. So we tested a bunch of different amplitude-related features, but the two ones that have performed the best, that are relatively simple to explain, are peak ground displacement, which I just showed you, and integrated absolute displacement, which is kind of shown schematically here, also corrected to 10 kilometers distance. You can see that the linear relationship is pretty stable relatively quickly, and if we compare directly to peak ground displacement, the saturation problem at large magnitudes is slightly less. There's still an issue, so this dot sitting way out here is Tohoku, and so it's not clear. It's not clear if Tohoku is an outlier or if using. I think I don't think it can just be this big of an outlier. I think if you're trying to record peak displacement-based measurement on using seismic data, you're at that magnitude, you're in trouble because it's not going to be sensitive to the really low frequency content. But in any case, this model works relatively well up to magnitude 7.2-ish. And so the PGD is used in a lot of real-time algorithms. IAD is used in almost none of them, and so it might be worth considering. and trying to incorporate this one.
May I ask a question?
Yeah.
What's the duration of these earthquakes? How does the duration of the actual rupture?
Yeah, well, I'll get into that. But yeah, that's the kind of the key question. It depends on the earthquake, the magnitude of the earthquake, and so the key question is whether you can distinguish between a large magnitude earthquake and a small magnitude earthquake at a time scale that's less than the source duration of the small magnitude earthquake. So I'll come back to that. So as I mentioned, we answered, we've tested a number of different features so far. The ones that are simple to explain are also peak ground velocity, peak ground acceleration. They also scale with magnitude, but it tends to be a little bit noisier than these guys. So now I'm circling back here. So instead of looking at different time windows, you might ask how these features, so something like peak ground displacement, evolves as a function of time. And so each of these curves, so this is a log-log scale, so log peak ground displacement, log time, plotting, and each of these curves corresponds to a different magnitude bin. So the yellow is the smallest magnitude earthquakes, purple are the largest magnitude earthquakes, at least that you can get a stable average for. And so you can see that the bin average value, so if you kind of average across magnitude, these are all separated pretty nicely at pretty short time windows. So this is a tenth of a second. And so this tenth of a second is much shorter than the source duration, even at the smallest magnitude earthquake in our data set. And so this implies that at least from a statistical perspective, there's some sort of determinism in the sense that the growth in the peak ground displacement is distinguishable, more rapid than the source duration of the smallest magnitude earthquake.
What does the Hokuoki look like on that plot? It's not there, right?
Yeah, it's not here because it has just one. That's a good question. I don't have it with me. It it doesn't look that different from this guy.
Okay, I mean that's what you would expect from the previous plots, I guess.
Yeah, it's back on the previous. Yeah, that's something I should add to this plot. But yeah, that's a good point.
But if you were to add a standard deviation on those,
yeah,
that's
that's the point. Is that on average there's some sort of determinism, but it's from an operational point of view, it's whether or not the variation is enough to be able to distinguish these things. So I mean, one thing that isn't done in practice but might be useful is to pose this more of as more of a classification problem than a continuous problem, in the sense that you might in real time we are more interested in knowing whether it's a really large earthquake or a large earthquake or a small earthquake than whether it's exactly magnitude 8.363. So. But anyways, yeah, if the variability within a given bin is larger than the separation, then it's challenging from an observational perspective.
I suppose the other classification could be, what is the maximum event this might actually be?
Yeah, exactly. Yeah, there's a lot of ways of thinking about it that aren't really done because they have the people that are working on this have their own challenges they have to deal with from a political perspective that a lot of the scientists don't have to deal with. But, they're very concerned with false alarms, and so there's always a social science trade-off that I don't have any expertise in and can't really help you with. So what's interesting is if you look at the initial growth pattern of these earthquakes, it's linear on this log-log plot, so it implies some sort of power law scaling. Also, if you kind of stare closely, the slope of these lines is slightly magnitude dependent, and I haven't really reconciled, whether that's like actually a real feature of the data or whether it's something related to a filter effect, and so I'm still working on that. But if that's true, that's also useful from an observational point of view. But this kind of gets back at the question of the rupture duration, is that the time scale, so you can see that these are linear for some time scale and they kind of roll off. And so the time scale at which this power law growth ends is actually, it scales self-similarly, which is a slope of 2 on this plot. And then this kind of time scale is of order the rupture duration. And so if we actually want to record what the actual peak ground displacement is, then we do need to record that long. But if we want that doesn't necessarily mean we need to record that long if we want to be able to distinguish a small magnitude from a large magnitude earthquake. Just for comparison, we can plot integrated absolute displacement. It has a pretty similar behavior in the sense that you can distinguish the values at short time scales as well as long time scales. It has a different slope because, this is kind of an integrated feature, so by definition it's monotonically increasing, but there's a break in the slope at about the same time scale. I actually copied and pasted these guys onto this slide, and it worked pretty nicely. So, just for comparison, if you want to see what I mean when this doesn't work as nicely as peak ground velocity and peak ground acceleration, you can see these guys are kind of all mixed up until a very long time after the time scale that exceeds the source duration. But it doesn't mean these aren't useful in a practical sense. It could be that they provide some value if you have a long recording time and a large magnitude earthquake. But that would be kind of follow-up research. It's not clear if there's any independent information inside of this that is not included in the peak ground displacement. And so the features I've discussed so far are these amplitude-based features, but you can also use something about the pulse duration to try and estimate earthquake magnitude, in the sense that large magnitude earthquakes should tend to have characteristically longer source durations or pulse durations than small magnitude earthquakes. And so this tau c feature is a kind of maybe the most commonly used one in real-time earthquake early warning. It's essentially a ratio of the RMS displacement over velocity. This formula is motivated by Parseval's theorem, because if we convert this to loosely speaking, if we convert this to the frequency domain, a bunch of things cancel, and it turns out this tau c is inversely proportional to kind of an average frequency content of the earthquake, at least within this source pulse. But in practice, at least for our data set, it doesn't seem to work very well. So there's a lot of scatter at low magnitude earthquakes. I think this is because these duration-based features are much more sensitive to integration artifacts and filtering artifacts than the amplitude-based features are. There still is a reasonable scaling in some regime here, but not all. It's not great, I would say.
Tohoku doesn't look anomalous in that.
Yeah, that's what's interesting is Tohoku doesn't look that anomalous, but part of that is just because there's so much scatter that the anomaly doesn't look very big. But anyway, so this is actually, what's troubling to me about this is that tau c is actually used in shake alert, but it could just be, I don't know. It's used as part of a much larger algorithm, but anyways. You tend to not care so much about the magnitude 4s, but anyways, but one thing we can do here is that, so if you go back and you look at what tau c, the formula for tau c is, it's some RMS displacement over velocity. There's kind of no reason why we can't just use the equivalent RMS of velocity over acceleration, because if we apply Parseval's theorem in the same way, we get the same sort of relationship. And as far as I know, no one's ever done this, but when we applied it to our data set, there's actually a much better behaved scaling that's much cleaner at low magnitudes. These guys at higher magnitudes are still outliers, but at least this is a pretty stable estimate for magnitude 4 to magnitude 7. One last duration-based feature I'll talk about is tau p, which is it's kind of analogous to tau ca. It's got this really complicated formulation, but it's based on the same principle that if you take some sort of velocity over acceleration, that gives you a time scale. And it scales, it's in use, I think not in California, but in some of the European earthquake early warning algorithms. It has a pretty good scaling up to magnitude 6.5. If you compare it directly to tau c is not great. Tau ca is better. Tau p, it's also pretty good, but it has a lot of, you can't really see the error bars very well in this plot, but there's a lot of scatter within an event, which makes it kind of problematic in a real-time setting. But anyways, these two have a pretty reasonable scaling up to magnitude 7, but there's still a question of these guys down here that we're really interested in from a hazard perspective. One last thing that's kind of interesting is that if you plot the time at which, if you plot tau c or tau p as a function of time for earthquakes of different magnitude, the time scale it takes to reach the kind of the peak value tends to scale with magnitude. So that's another thing that's I'm still studying more closely, but there's also, you see this kind of mix up at high magnitudes. That's what saturation looks like in this space. So I'm not sure if this is really helpful or not, but it's worth considering. So just to recap the results here, we looked at both amplitude and duration-based features. And so simple ones like peak ground displacement and integrated absolute displacement, they're easy to compute. Everyone understands what they are. Their growth curves are suggesting that there is some sort of determinism, at least in a statistical sense, because you can differentiate those curves at a time scale that's much less than the source duration. That doesn't necessarily mean that there's a practical determinism for an earthquake early warning algorithm. If you want to compute I think this is a little bit of a confusing point, but if you want to compute the actual peak ground motion, you do have to record that long. But that doesn't mean you need to record that long to forecast the event size. The duration-based features, at least this kind of improved tau CA and tau P max, they can also be used to provide magnitude estimates, but I think they're more sensitive to processing and filtering. And so one of the things I'm going to be working on going forward is, I guess that's a different slide, but one of the things I'm going to be working on going forward is really optimizing that processing workflow. And so from a physical perspective, what this determinism, we're interested in this question of how early in the rupture process the large and the small events are actually distinguishable. If it's possible to distinguish those on a time scale that's more rapid than the total source duration, it must be that there's something about the source properties that are occurring at the hypocenter that are predictive of the final earthquake size. And so if we can derive features that measure that initial energy flux or the rise time or the slip rate at the hypocenter, then it could be that we can actually make some progress towards understanding these deterministic, whether or not ruptures are deterministic. But the work is still definitely in progress at this point. So I think the first step is just to really make sure we have the kind of the best processing that we can do in terms of filtering, data selection, and site-specific corrections. And then this is where the kind of the real machine learning part is going to come in, is in the model development, developing models that combine different features to provide the best estimates that hopefully don't saturate as badly at high magnitudes. Trying to understand if there are features we're missing, which I'm sure we are, but whether there's a lot of added value in those. What I'm working on right now, talking with some scientists next week actually, is getting a hold of the real-time geodetic data streams, because those are sensitive at low frequencies. That will be really helpful for the large magnitude earthquakes. And then one question that I think is completely understudied is this question of regional extrapolation. And so if you develop some sort of earthquake early warning algorithm for some place like Japan and you want to apply it in Chile, that it might not work very well, and that's okay in Chile because we have data in Chile and we might be able to just train an algorithm there. But it has a lot of relevance for Cascadia, where we don't have, we're trying to develop earthquake early warning algorithm offshore Oregon and Washington, and we have almost no real-time data. And so any algorithm we're going to apply there is going to be developed somewhere else. And so we really have to understand what the uncertainties are when you extrapolate like that. So I'm definitely out of time at this point, and so I'll leave my recap slide up here. So I'm happy to talk with you about ground motion modeling or rupture determinism, any questions related to that, or any of my other research projects. I'm really excited to have the opportunity to come visit you guys in Boston. So thanks for your attention.
We have time for 2 short questions, if someone.
And then I'll be here this afternoon. So.
I'm not sure it's a short question, but are the 2 end members basically the the early warning is what happens in the nucleation phase itself versus the pre-stressing on the fault. And I'm wondering if you were to somehow try to characterize the fault situation before the earthquake happened, would you have a better way of knowing that a particular nucleated event is likely to rupture the whole thing or only rupture a little bit and then peter out if you knew what the fault looked like?
Yeah, so I mean, I guess from that's a really hard question to answer from a observational point of view because we can't really measure that. It's the type of thing that that you can make a lot of progress towards in the laboratory, in the sense that you can actually go in and like characterize the state of stress on the fault before an earthquake, or you can try to. The closer you can get into actually recording, or measuring the state of stress and the stress distribution on the fault before an earthquake occurs, the better chance you're going to actually be able to sort this out from a physical as opposed to an observational point of view.
But the earthquake simulators.
Yeah, those types of, well, I mean, it depends on how much you trust the physics of the earthquake simulators, but I would say from an observational point of view, it's a really hard question to sort out in terms of like actually proving or disproving one of those hypotheses. I would say that if you look at the laboratory data, there's almost universally precursory activity before a slip event in laboratory experiments, and so whether that's kind of universal in the real Earth and we're just not recording it all the time, or whether real earthquakes differ from laboratory earthquakes is kind of an open question. But I'm sure you've seen, it seems like there's a paper published every week of a new type of precursory phenomenon preceding the Tohoku earthquake. There was just one last week on there's a gravitational precursor, and so could be. Yeah, I don't know.
It's only another 150 years to find out.
Yeah, so, but I mean, some of these are testable, and some of these are not, and that's.
Is there any way to bring historical seismicity in, kind of as a Bayesian prior? You say that in this area we expect these kind of earthquakes, and therefore when you get something, you could narrow the range of uncertainty based on. You didn't use anything about the location.
Right.
So you might expect. I mean, nobody expected Tohoku.
Yeah.
They should have, but they didn't. I mean, historically, I think they have to go back a long way to know to expect it. But you do have catalogs in some places that are somewhat, and you could boost the catalog by what you expect based on tectonic.
Yeah. There definitely is a way to. You can actually. I think the Bayesian perspective is really, if we kind of come back to this workflow here, the Bayesian perspective, and you can incorporate kind of whatever you want into your prior, including historical seismicity, is really useful in kind of this state. Once you're really into the hardcore data processing, you can use it. You can use a Bayesian framework, but you can use it. Essentially the stuff that I'm describing today is more of the kind of, in a Bayesian sense, you're describing likelihood computations, but when you're trying to estimate the final distribution of magnitude, you can incorporate anything you want, including the historical seismicity. And in fact, I think some real-time earthquake early warning algorithms, which sound like a great idea in theory and don't tend to work very well in practice, are ones that try and estimate the finite fault model in real time. And those, I know of at least one that uses essentially a prior on fault geometry. And I don't think that that's actually the big issue with it. The issue is that it works. They tend to work really well when you have a really good recording distribution, and the earthquake is within network, and you get a really good spatial pattern, and then it fails spectacularly if the earthquake is not located in that sense. But yeah, you can use. This is what I presented today is a very seismic data heavy data processing point of view, but there's really a lot of value added in bringing in as many types of data sets as possible. So the GPS is another observational data set, but equally important is trying to understand what tectonic environment you're in and how you'd expect a distribution of event. What would a magnitude 9 in Cascading actually look like? And they've simulated it, but It's the type of thing is worth thinking about when you're, especially when you don't have to worry about these things when you're really data rich, but you do when you're data poor at high magnitudes, and so.
All right.
Doug Miller says, great talking to chat.
Who is that?
Doug Miller.
Okay. Oh, great.
You've streamed.
Interesting.
All right. Let's thank the speaker one more time.